here is where the electric potential can really make life easy for us for various calculations. What I've got right here is a 9-volt battery, and the positive terminal is connected to this plate over here. The negative terminal electrically connected to this plate over here. The distance between them is D, which for this example, I'm going to make it a 9-volt battery, and the plates are separated by 0.9 meters. What's the electric field strength between these two plates, and which way does it point? Let's do the last part first. Which way does the field point? It'll point in the direction that a positive charge would move. A positive charge placed right at this plate between the two would accelerate downhill to the negative plate. It's attracted to the negative plate, so it would point to the left. What is the magnitude? Well, if we assume it's a uniform field in here, we just use delta V is negative ed. The field itself would be negative delta V over D, but the delta V is negative itself. So the magnitude of the field is the change in potential from this plate to that plate, which is 9 volts, and you divide that by the distance between it, 0.9 meters. That is 10 volts per meter. Do some unit analysis, you will find that 10 volts per meter is the same thing as 10 newtons per coulomb. It is a valid unit for measuring field. And as we said, it points towards the negative plate. So you could use delta V equals just ed if you are just looking for the magnitude in the electric potential change. But then you'd have to realize that the positive charge goes downhill, so plate B is at a lower potential. Here's another example. A field strength of about 3 million newtons per coulomb is required to ionize air. What is the voltage difference between a charged flat conducting plate and a parallel flat grounded plate if there is a 0.1 meter long spark between them? Well, hint, we know the field strength. We know the distance between the plates. It's pretty easy to figure it out. We know the field strength, and that this is the field that's necessary for air to ionize, 3 million volts per meter or 3 million newtons per coulomb. Since there's a uniform field, ignoring the edge effects, magnitude, again, magnitude delta V is ed. Delta V is E, 3 million volts per meter times 0.1 meters, 300,000 volts. And if you get a 10 centimeter spark from a Van de Graaff generator, that means it's at 300,000 volts compared to ground, which is where you are standing.